ready.
Yes, ready.
Yes. Yeah, first I think you are still stay here. So yes, you will miss the coffee. Yes.
We have a 10 minutes break. Information
Okay.
to change the computer, and 10 minutes after the finish of your presentation, we
Okay.
will continue with the next session.
Okay.
So please enjoy
Yes.
your
So I will talk as quickly as possible. So yes.
Don't worry, you have
Okay.
all time in the world for your presentation.
Okay, thank you very much. So my name is Guocai from Sandvik in Sweden. I'm also a adjunct professor in Linköping University. My presentation today is microstructures and hydrogen embrittlement fracture mechanism in 7,4 pH steels. First, I want to acknowledge my colleagues, Dr. Tomas and Antonsson. Then I also acknowledge my courses from Sweden, Dr. Sten, Wessman, and Miss Lena, Ryde. So my presentation will study first the introduction of 7,4 pH materials. Then we'll talk about material and experiment work. Then provide some results and discussion. And finally, I will conclude my presentation. 7,4 pH actually is a well-known material. So it is a precipitated martensitic hardened steel. So with high strength and high ductility. So they have a high performance and widely used in different industries. But it was found this material is suspected to hydrogen embrittlement. So here I show one example is in pressure safety valve, so in oil gas industry. So you can see crack here, and also it's a very typical intergranular crack. Then with a typical hydrogen void. So the objective of this study, if we can find some heat treatment, then can reduce this hydrogen susceptibility. Then also try to understand what is the hydrogen embrittlement mechanisms in this areas. So what we do, so first we use a very standard material. So it's a bar material, so it's a solution annealed with this standard composition. Then so here is a microstructure, is quite homogeneous without so much texture in this material. Then with the martensitic loss is 0.36 micrometer, so it's quite a good microstructure. Then we use this as received material, perform 3 tempering. So 510, 566, and 621. So why we choose these temperatures? This is according to American definition. So yes, this type of number here. So then after that we check the microstructure. So here is from as received is the main martensitic and have some niobium carbides. Then after tempering, then we found that 3 new phases. One is a couple-rich phase. So, but it's the influence of temperature is very small. Then is M23 carbides. So the temperature is also small. So what happened is just the austenite phase. So with the increased temperatures, and austenitic phase increase. Then we can find this where this austenitic phase. So it's mainly it's a green boundary, or it is a martensitic loss boundary. So they are quite important. I will talk it later. So the testing facility, it was done at Sweden. So with this SSRT standard, not standard, it's type of testing usually used to in charge hydrogen. Then we use this parameter as 3.5% sodium chloride. Then here is important. So 2 current. One is 0.05, another is 0.2. then with the strain rate 10 up to -6%. So here is the result. So first, this curve shows the I call the reference without hydrogen charging. So we can see this is as received. Then here is tempered. With temper, then the elongation increase and increase with temperature. Then this is just after hydrogen in charge. But here is only current is 0.05. So we can see that for this as received material, so now the elongation is a significant decrease from about 9.9 then to about 3. So, but interesting with the tempering, then the elongation increase. Then here is 0.05, then increase the current. Now the elongation still decrease. But interesting is that after tempering, then the elongation increase. Then is without, especially when temperature is below 566, then the elongation increase, but without sacrifice so much strength. At 620 degrees, and the elongation now is almost similar as received material. So that means with the heat treatment tempering, then we can reduce hydrogen embrittlement susceptibility, but maybe not totally avoid. Now we try to check the mechanism. First, from fracture we can see as received material with increased temperature, then we can increase the contraction here. But with in charge, now we can find some areas they have hydrogen embrittlement. Then with the tempering, then the contraction also increase, but still have some hydrogen embrittlement. So with the decrease the current, then increase the contraction. Now if we have a close look of this area, what happened? So we can see this 6 type of fracture. So for this fracture is from the as received material with the high current. Then we can see it's mainly intergranular, but with some cleavage. Then with the tempered material, now we can see, so it's mainly cleavage, but still have some intergranular. And the increased temperature decrease the intergranular cracking. Then it's 621 now ductile fracture can be observed. So it's quite interesting. So people usually talk about intergranular cleavage, but in which conditions? So I think it gives a chance. Then with the decrease of current, so now we can find a type of hydrogen void. But it's still we cannot explain why the difference here. But it's only observed with the low current. So by summarize all this, we found that so in this case, intergranular cracking is the most dangerous. Then come to cleavage. Then with the increase of FCC phase, then maybe we can increase ductility and reduce the susceptibility of hydrogen in this material. Now we have to increase to study the mechanism. So we just see to the cross section. Then we can find that this area is mainly the hydrogen embrittlement area. This is ductile area. So we can take a small area with the EBSD. We can find that with the chem, then we can find the stress concentration. They are mainly in some inclusion, austenitic phase or martensitic loss. Then we try to find what happened with hydrogen. So we found that there are 2 types of void found. One is in this area. So this area actually is near the surface, sample surface. So this is a plastic deformation zone by machining. So they introduce a lot of dislocations. So we found a lot of very small nano voids in this area. Then in the matrix, so we can find also a lot of voids. They are mainly formed either at precipitates or at grain boundary or martensitic loss. So that means hydrogen can introduce diffusion into the materials and form a lot of voids. Then to study the crack initiation. So actually we found some interesting things. One is that, from plastic deformation zone by machining, so we can find some, here is a short crack. So we can see, actually we can see this is a zigzag area. So this is actually the coherency of normal voids. But a crack initiation mainly, it has a surface defects, you can see. Then inside, now I think here. Then inside we found some interesting also. So this is a martensitic less. So actually crack initiation in this area from one oil we can say it's grain boundary, but I think it's martensitic less. So study with interaction here, but stop is here. So this is a hydrogen embrittlement crack initiation. So this caused the cleavage here. So this is a type of cleavage in the material. Then we try to find the crack propagation. What happened for crack propagation? So we found that this is a crack path we can see here. Then we have this is actually from ECCI pictures. So we can see that. So here is a grain boundary or a martensitic phase boundary. We can see that. So this is mainly a coarse intergranular cracking. Then from here to here, it's more or less cleavage. Then to another grain boundary, it stopped. Then will crack propagate around the grain boundary. Then to initiate another cleavage, then and so on. So actually, crack propagation originally started from a boundary, either from grain boundary or from a martensitic phase boundary. Then cause cleavage or intergranular crack. So for some cases, you can find both a combination of intergranular and cleavage crack. So here is the mechanism for your hydrogen embrittlement cracking in these materials. First is hydrogen trapping. So either it's a dislocation, the slipper bands, or it is the interaction of dislocation, either in intermetallic phase. Then form a non-void. Then due to local stress concentration, it's a grain bound, it's a void, then will cause crack initiation. Then especially when the stress concentration is high enough. So I just show this is critical stress we need to study. Then causes the crack propagation. With that, I will just avoid that. So I think thank you very much for your attention.